Have you ever just stopped and thought about how a child learns to talk? I mean, it's kind of wild, right? They go from just babbling to making these complex sentences in just a couple of years. It's got to be one of the most amazing things a brain can do. So today, we're going to dive into what's known as the gold standard of learning theory to try and figure out how a child's mind actually gets so good at language.
So this is the big puzzle. Really think about it. A kid hears this jumble of words and sentences, and a lot of it is incomplete or grammatically messy. And somehow, from that limited, kind of flawed information, they figure out a whole system of rules. A system so complex that actual linguists spend their whole lives studying it. So, how on earth is that even possible? This is the question that's been bugging scientists for a long, long time.
All right, to get to the bottom of this, we've got to put on our computer scientist hats for a minute. We need a formal model, a really precise way of looking at this learning puzzle. And our journey is going to take us all the way back to the start of a field called computational learning theory.
Our story really kicks off with a computer scientist named E.M. Gold. Back in his really important 1967 paper, he wasn't just thinking about language. He was trying to build a mathematical model for learning, period. He wanted to know in a super precise, formal way what it takes for any system, whether it's a computer or a kid's brain, to learn a set of rules just by seeing examples.
So to model this whole process, Gold imagined this theoretical learning machine. Now, we're not talking about a physical box with gears and wires. No, it was an abstract idea, a perfect, logical set of steps that could, in theory, pull off the same incredible feat that a child does when they learn to speak.
The main idea he came up with is called identification in the limit. I know, it sounds a little technical, but the idea itself is actually pretty simple and kind of beautiful. Think of it like tuning an old-school radio. You're twisting the dial, right? You get a bunch of static, you land on the wrong stations, you're making a new guess with every little sound you hear. But eventually, if the language is learnable, you lock onto the right frequency. The signal comes in crystal clear and you stop turning the dial. You've found it. You've got the final, correct answer. This whole process basically turns the learner into a detective. Every sentence the kid hears is a clue. And from that clue, they form a hypothesis, a theory, like, okay, to make something past tense, I just add ed at the end. But then they get more clues. They hear someone say, I ran, not I runned, and whoops, they got to revise that hypothesis. So they're just guessing, testing, and revising over and over again until they finally crack the case, the correct grammar of their language. And this brilliant model forces us to ask a couple of absolutely huge questions. First off, what is it about a language that makes it possible to learn this way, just from hearing people talk? And second, what does this tell us about the program that's running inside a kid's brain? What are the built-in tools that let them pull this whole thing off? So Gold gave us this perfect, logical machine. But, and this is where it gets really fascinating, when scientists started comparing this ideal model to actual kids, they found out that the road to mastering a language is not a straight line. Not at all. In fact, it's full of these weird but incredibly important glitches. And here's the crucial idea, and it's totally counterintuitive. We usually think learning is about constantly getting better, right? Just a straight shot up. But the data shows something completely different. Sometimes, to really truly master something, a child's performance actually has to get worse before it can get better. Okay, let's take the verb go. It's a perfect example. A 2-year-old might correctly say went. They've probably just memorized it like it's a single word. But then, around age 3, they start saying stuff like go it. Now, to us, that looks like a mistake, a big step backward. But what's really happening under the hood is incredible. The kid has just discovered a rule, that you can make verbs past tense by adding ed. And they're so excited about this new powerful rule that they use it for everything, even when it doesn't fit. Then finally, by age 4, they figure out the rule and its exceptions and they go back to saying went, but now they have a much, much deeper understanding. This whole pattern is called U-shaped learning. And get this, the analysis of these learning models proves this isn't just some quirky little phase kids go through. This whole process of unlearning, of ditching a simple memorized word for a general rule, even if it causes mistakes, it's often a mathematically necessary step to get the whole system right in the end. The mistake is actually a sign of progress. How cool is that?
So we know that making mistakes is a key part of building that internal rule book. But what happens when the rules that kids hear from the outside world are themselves messy and inconsistent? How do they deal with that?
Well, this leads to a really fundamental shift in how we see this. A child is not a passive little tape recorder just absorbing everything they hear. Not at all.
They are an active editor. They take the inconsistent, messy language that we adults use and they clean it up. They actually impose order on the chaos. They regularize it.
And one of the super powerful strategies they use for this is called frequency boosting. Imagine a parent uses a grammar rule correctly most of the time, but sometimes they're inconsistent. A kid will actually pick up on which rule is more common, and then they boost it. They start applying that dominant rule almost all the time, basically ignoring the messy exceptions they hear. They're betting on the pattern, not the noise.
Now, all of this seems to point to one big conclusion, that our brains must have some kind of pre-programmed language rules built in. But what if that's not it? What if the answer is something way simpler, and maybe even more profound?
So on one hand, Gould's model kind of implies we need some sort of language acquisition device that's already loaded up with specific rules. But there's this alternative idea, the simplicity principle, that offers a really fascinating contrast. It suggests that maybe the only innate tool a child needs is just one powerful drive. Always choose the simplest, most compact explanation for what you're hearing.
So this ideal learner isn't born with a grammar book in its head. It's born with a preference for elegance, for efficiency. When it's faced with a bunch of different possible grammars that could explain the sentences it hears, it'll always pick the one that can be described in the shortest, neatest way. It's kind of like an algorithmic Occam's razor. The simplest theory is the best one.
And so that leaves us with this final, really deep question. Is the miracle of learning language a result of some preloaded grammar hardwired into our biology? Or is it the product of a much more general, more fundamental principle? A brain that is just a beautifully elegant machine optimized to do one thing: find the simplest possible pattern in a complex world. The search for that answer, well, that continues to be the gold standard of learning science.